So I'm recording this as an example introduction to Haskell for 538. I don't mean this to be a full explanation of the language, but a guide to getting started with a relatively different language than most of the programming languages you've probably used before. To start, you have to install Haskell. It does not come default on most computers. There are a few. So if you do not have it, you can go to haskell.org/ghcup and download ghcup through the appropriate command. If you're on Linux or Mac, you can just use this simple terminal command, or if you're on Windows, they have a separate, slightly more complicated command. Once you have it installed, you should be able to run ghcup and then the terminal user interface specifically. I'll make this a bit bigger, which will present to you some form of this interface where you can navigate the various versions of these systems. So I'm not going to go into high-level detail here. The important thing is that you have Cabal and that you have GHC. I personally use 948 and 310. These are just the recommended settings, so that's what I follow. You will be fine if you do the same. If you have a more recent version, you might run into a few issues, but nothing you shouldn't be able to solve. Okay, then we can open up intro.hs, and this file is provided on Canvas. If you go to Files, Code, or HS Code, and then intro.hs, you'll have a file that looks something like this, and I'm going to walk through exactly what's happening and how we can read a file like this and interact with it. So to start, we have the declaration of a module, and every Haskell file is going to be a module that you could load and use and import other features from. Prelude is it's the standard library for Haskell, it contains all the key utility functions that you might want to use. We are importing that so that we can use standard library abilities, but we're actually not importing a specific class called either, and that's just because we will recreate it ourselves. Now to start, Haskell looks relatively straightforward. We can create a variable declaration just like you would in a traditional language. So we can say x is equal to 2, and now we have a variable named x, which is equal to 2. But despite the fact that this is called a variable, it can't actually change. So it's actually an immutable. And this is a core principle of Haskell. They don't want their variables to change. Immutable things allow you to make stronger guarantees about the values. So if we, for example, uncomment our x equals 2, our x equals 3, and reassign x to be 3, this is actually going to raise an error. And to show you that, I want to pull up our GHC. And GHCI is the interpreter for Haskell where you can actually interact with these things dynamically, and we can load in our intro file by running GHCI intro. And this should pop you into an interpreter, something like this, and then we can ask for the value of x. Okay, so x has the value 2. Now if we go in and uncomment that and say x is equal to 3, and then we reload with :r, so this is going to reload intro HS, it's going to give us an error and say, you cannot redeclare x. So, okay, we can't do that. But that can be kind of restricting and sometimes annoying when you want to have multiple variables with the same name. But if they were in different scopes, traditionally that should be allowed. So what you can do is create a let scope where we can say within this value, within this expression, x is going to be equal to 44. And that's shadowing the above value of x. So we haven't overridden x. We've created a new version of x that within this piece right here has the value 44. So if you read this in English, we're saying let x equal 44 and z equal x minus 2, in the expression z times 2. And it's important to ask yourself here, what is the value of example 0? Which hinges on which value of x is used in this part of the expression. So it'd be good to, come to a reason for this yourself, but we can go ahead and just check example 0. Oh, we need to reload after, and then example 0. And we see that the value is indeed 84. So we've created this new scope where x is equal to 44 and used that value of x here and then get 84 in the final answer. A weird piece about Haskell having immutable values is that variables are actually order independent. And what that means is that we can create a variable a that depends on y. For example, if y, then a or b. And what you'll notice is we haven't yet declared y up above, but we will declare it sometime later in the file. Maybe it's the next line, maybe it's 10 lines down, or at the very end. And that's okay, because Haskell is not reading line by line and interpreting line by line. It's able to do larger scale processing to figure out y at some point will be equal to 0 or equal to true, and therefore at every point in time is equal to true, because these variables cannot change. So we can then inspect the value of a. It's the character a. Programming in Haskell is all about expressions, and this is what you'll read online a lot when people talk about it. The purpose of writing code in Haskell is to manipulate and transform expressions into their corresponding values, to interpret an expression into its value. And so you'll see that the difference here is it's a transformation. We need to actually evaluate the core expression to get the value, but they are functionally equivalent. And this builds from lambda calculus. Because everything's immutable and everything is an expression, we can just do substitution, beta substitution, just like we have been doing in lambda calculus. And indeed, that's the main backbone of evaluating in Haskell. So if we have some expression such as let x equal 42 and z equal negative x minus 2 in z times 2, we can just rewrite and substitute the x for the value that it has, which is 44. And so then z equals 44 minus 2 in that, and then again replace z with the value that it has, the expression that it has. And we end up with 84. Types are very important to Haskell. Everything has a type. There's no point in time where you can be unknown in your type. So to start, we have some relatively straightforward types. We have integer types, and you can see this : : that's saying the variable int val has the type integer. It's somewhat similar to Python syntax with type hints, where you would say like int val int equals 32 or something like that. So colons are for types. And then we could actually assign the value of it just after. Int and integer are similar but slightly different. Int is word sized, dependent on your machine, and integers are arbitrarily large. We can also create a double to use floating points. We can have characters, and you'll notice we've inlined the type annotation here. And we can have strings, which are lists of characters. You can create a list of an int, just as you would in normal language. And you can use booleans. So you've got all of the normal primitives. Not that insane of a language. One thing you might have noticed is that we didn't actually give a type to the double, and that's okay. Haskell knows that we are adding floating point numbers together here, and the result will be a float. And then when you multiply by 3, you're still going to have a float. And this is called type inference, and we're going to look at this later this week of how does Haskell do it. One of the key functionality or features of the GHCI is that you can use :t to inspect types. So for example, we can do :t of, we have II, and that will tell us it's an integer, or :t of DBL, and that will tell us it's a double. At any point in time, you can ask, what's the type of this thing? It's generally recommended that you specify types if they are non-obvious, and the reason it makes your code easier to read, and type hints become, or type annotations become easier to use, your IDE is happier, things like that. And an important thing to recognize here is this is different than not specifying types in JavaScript. In JavaScript, if you don't specify a type, we don't specify types, and the result is at runtime we figure out what is the thing that this object is. Is it an integer? Is it a string? Is it a complicated object of other sorts? Haskell is doing all of this at compile time to figure out what are all the types of your various values and are they behaving properly. There are no implicit conversions, so you cannot perform operations that would require you to implicitly convert. So if we did, for example, II plus DBL, this would be a type error. You cannot add an int and a double. You could first manually convert the int to be a double and then perform the addition. But Haskell won't do it for you. All right, we do have standard arithmetic, plus, multiply, etc. And we're going to talk about how those work in this language later on. Moving on to functions. Functions are the biggest piece of Haskell. It's a functional language. This is what everybody cares about. So functions have a type. Every function has a type, and you write them by using these arrows. So for example, we might have a function, pos, which determines whether an integer is positive or negative. So it takes in an integer and it returns a Boolean, true or false. And we write that by saying integer goes to Boolean. Convert an integer into a Boolean. We can also have greater than. Greater than is a function that takes in an integer and it returns a function that takes in an integer and returns a Boolean. Another way of saying that is that it takes in two integers and returns a Boolean. But with Haskell, we have currying, where you can take in a single one of your parameters at a time and return back a partially applied function. So positive, and this is where the syntax starts to get a little wild. Let's look at this first example. pos is a function that takes in a single input x, and it returns the result of x greater than 0. So just going over that again, we have the name of the function, the parameter to the function is equal to the return value of the function. This is our structure, which is very similar to, we have a lambda that takes in a parameter x and has a return. That's not by accident. These things are built, Haskell is built on concepts from lambda calculus. And this becomes very clear when you look at another way to write the function. So greater than is a function that's equal to a function that takes in x and y, and it returns x is greater than y, which looks just like its lambda calculus counterpart. We use the arrow here instead of the dot, and other than that, it's identical. Function application looks just like lambda calculus. So we just use a space to say, here's a function, here's its argument, what's the result? And we can actually look at this. We can say, is 33 pause, has the result true? Similarly, we can look at the types of these functions. So the type of pause is integer to bool. And I do want to point out the purpose of these functions is to provide a transformation. It's a meaning. It's not exactly a function like you typically have in another language. Although these days there's more blurriness in that. So if you think about it from a mathematical transformation function, a function named f is of type a to b means that for every element of a, think for every integer, f of that integer is equal to y for some element y in b. Or if it doesn't, this is not the function doesn't hold. So for every integer, we can create a Boolean. That's what pause is doing. That's what pause means. For every integer, we can create a Boolean. Functions can take multiple arguments, just like in normal languages. So this arithmetic function can take in 3 different integers, and it returns a single integer. But we don't have to pass all of those parameters at once. So breaking down the code here again, we have the function name takes in 3 integers, x, y, and z, and is equal to a single x times y, or times y plus z. We can pass a single argument at a time. So we could create an add function that takes in x and y, and it returns x plus y. And then we can compute 5, which is add 3 and 2. But we could also create an add 3 function that only passes in the 3. So we have partially applied add. And the result is a function that takes in a single integer and will return a new integer. This more generally means Haskell, all Haskell functions take 1 argument. And if you want multiple functions, multiple arguments, all you do is you return a function to handle the next argument. This is exactly what we do in lambda calculus as well. And so when we put parentheses in, we would say that add is a function that takes an integer and it returns a new function. The new function is a function that takes an integer and returns an integer. And this scales to however many inputs you want. So add 4 things, takes in 4 floats, and returns a single float. But really, it takes in 1 float and returns a function that takes in 1 float and returns a function that takes in 1 float and returns a function that takes in 1 float and returns a float. We can do complicated data types, just like in other languages. We can create a void type called unit, We can create tuples, where you kind of bind together types, values of different types, perhaps. So we could create a tuple of an int, a character, and a double. And then you could actually use these to create multi-argument functions if you wanted. or create the appearance of them, where you create an add function that takes in a tuple of ints and returns an int. This is relatively irregular, but you can if you want. And then to approximate traditional languages, you can add 3 and 5 by saying fun add of 3 and 5. And then it almost even looks like you have the parentheses of a normal language instead of the space doing the function application. But I'll warn you, that's not what's happening. The space here is the function application, and these parentheses are just creating the tuple. You have lists, just like another language. We can create an int list, 1, 2, 3. We can also use what's called the cons operator, this single colon, which prepends an element to a list. So if we create my int list triple prime, we could do that by saying 1 prepended to 2 prepended to 3 prepended to the empty list. And so that's going to take 3, add it to the list, then add 2 to the list that contains 3, and then add 1 to the list that contains 2 and 3. So here we see cons then is taking a single int, a list of ints, and returns a list of ints. But it's actually going to be generic, and it's going to let us do this with ints and strings and characters and whatever other data types we want. We also have the ability to concatenate. So if we have 2 lists, we can concatenate them together with ++. Great. Empty lists do sometimes have a type. They always have a type, but they sometimes have an explicit type. So we can create an empty list of booleans or an empty list of characters. Even though these look the same, they are actually different. You cannot create heterogeneous lists. So you cannot have a list of 1 and 2.3. That's not going to work in Haskell. You could instead use a tuple if you just had a fixed size. Or we can create fancy type wrappers to create things that might be integers or might be floats. And we'll look at that. And this next section is really where Haskell starts to get powerful and interesting. And it's around these abstract data types. This is how, in Haskell, we can create complicated data structures. So I'm hesitant to say it, but think of an object in an OO language where you want to wrap multiple pieces of data together. Now, the object in an OO language wraps data and it responds to messages coming in. That's not what's happening here. This data type is not going to respond to any messages, but it is wrapping up data. So we can put multiple pieces of data together and we can create things like cars or points or whatever you want. So the way that we do this, and this can be a little tricky, so let's look at every word here. To start, we have the data keyword. That's saying create a new data type. Then we provide the name of our type. So I want to create a new data type called pair T. Then we have what's called the constructor. And the constructor you can think of as a fancy function which is going to return something of type pair T. So pair C is a constructor, a fancy function, and it's going to store 2 integers. So you can call pair C with 2 integers, and the result will be a pair T. So if we wanted, we could create my pair is of type pair T, and it's equal to pair C 3, 4. And here I'm wrapping up 3 and 4 into a single data point. We can have multiple constructors. So up above we had two integer types, two integer values creating our data type. But here we can have a point with a constructor for Cartesian points and a constructor for polar points. Then you can create points using either Cartesian or polar, and the type of the point is going to depend on the constructor that we have used. We'll see an example of that in a minute. You can also create a data type which doesn't store any values other than the constructor itself. So we could create a color type which has five different constructors: red, green, blue, indigo, violet. And then you could create a color red is equal to red. So how can we use these things? Well, to start, these partially apply just like any normal function. So you can create a partially applied constructor by passing only one of the data values that it needs. My pair prime will create a pair t from an integer. And then this is where we start to see the power of these data types. We could have a function called getX, which is going to break apart, it's going to deconstruct the data inside of the type. So our function getX, first of all, it takes a pair and it returns an integer. So pair is the argument, and then we can use a case of statement to break it apart. So the case of pair, where we want to destructure the type into its components and return x. So on the left, we have the structure that we want to match against, and on the right, we have the return value. Let's see another example of this that's more interesting. So we can create a two-Cartesian function that takes in a point and it returns a point. The goal is to convert the polar points into Cartesian points. So two-Cartesian is the function name, point is the parameter, and then break apart the different cases of points. If it's a polar point, polar with r and a theta, then return a new Cartesian point with these values. R times cosine of theta and r times sine of theta is the mathematical conversion for polar to Cartesian. And then anything else, return the original point. And if you think about it, there are only two options. We either have a polar point, which we want to turn into the Cartesian version, or we have the Cartesian and it's already done. It already is Cartesian, so just return the point back. So this underscore is a special case, just empty, match anything. And we'll see some other syntax for writing this as well later. We can use this to create some fun recursive expressions as well. So we could create a tiny language, a new data type expression, and this expression can either be an add expression with two expressions underneath it, a multiply expression, or a constant, an integer. And we could create an evaluator that turns an expression into an integer. And here's a powerful pattern matching technique that we can use. So to start, we're saying eval, if you pass it as a parameter, a constant expression where the inner value is n, return n. And n, we know, is an integer, because a constant expression stores an integer. Now, if you pass in an add expression, we want to handle this slightly differently. But an add expression contains two expressions on its own. So if we eval e1 and add that to eval e2, well, each of those evals is going to return an integer. And we can do an integer plus an integer. And so we can recursively define this. We have our base case where you have just an integer expression. And we have our two complicated cases that are recursive on adding and multiplying. We've defined one function here, but we've defined it three different ways, depending on what type of expression is passed in. Is this a constant expression, an add expression, or a multiply expression? So we can use this in other ways as well. If we go back to our Cartesian example, we could define two Cartesian. When you are passing a polar point, that's going to be equal to, and we can just pop this onto one line, Cartesian of the x component and the y component. Otherwise, it's the x that you passed in. It's whatever you gave it. And the only time you would have this case instead of the upper one is if x is Cartesian. Now, I want to put a caveat here. Order matters in these definitions. If we have something that generically matches everything, that's what's going to be checked first, which means that it's going to match everything, and anything that comes in will be returned. We would never use this second definition. Now, I believe if you have something like this, and we reload our module, we're actually, I think, going to get a warning. Yeah, there you go. So pattern match is redundant. And this is just a warning. It's not, breaking our code. But it's letting you know this one's never going to happen. So maybe you want to get rid of it. But obviously we don't. We just wanted it in the other order. All right, skipping ahead a little bit here, we can come up with some interesting recursive functions this way relatively easily. So factorial, if you pass it 0 is equal to 1, and otherwise it's equal to n times factorial of n minus 1. Now, you might notice immediately, or after looking a bit longer, what happens if we have a negative value. It is actually going to go infinite. It's never going to stop. So we can use guards to protect ourselves from this. Here's another syntax for defining patterns that we want to match on. So we're saying factorial takes an input n, and if n is less than or equal to 0, return 1. Otherwise, it's equal to n times factorial n minus 1. So we have this weird construct before the equals sign, this vertical bar that's called a guard, where we want to put some sort of conditional expression in here. All right, yeah, guards are just predicates. They're just conditions. Okay, we can create recursive data types as well. So we can create a data type int list, which is either an empty constructor, doesn't store any data, or it's a cons constructor with an actual int and recursively an int list. So the type is defined in terms of the type. What that means is that we can have an empty list, which is just the nil value, the empty, or we can cons an integer with a list. And that list is itself a cons of an integer and a list. And that is a cons of an integer and, in this case, the empty list. And then we can write functions on these recursively defined data types. So sum of int list takes in an integer list and returns an integer. And I would challenge you to pause the video, try to write what this function would look like. What should sum of int list be? And we can start, I actually would not start with that line, sum of int list. What are the different options for the parameters? Well, it's an int list, so one option is that it's the nil value. And if you pass me the empty list, the sum of that list is just 0. And then we can create the sum of int list on a non-nil value. So we had two options. We had nil or we had a cons. And if we had the icons of some integer n and some list ls, well, that's going to be n, the integer, plus sum of int list on ls. And we might want to put parentheses just to be clear about the order here. So we're recursively solving this. If we look at our solution, looks like, okay, so we handled the error case a little bit differently, but perhaps that doesn't matter. So then we could check this to make sure that we actually have this. If we sum our list, we do get 6. I'm sure that we will, so we don't have to. We created an int list, but we could also create a character list the exact same way. This would get kind of tedious. We want to create reusable data structures. Whether it's a list of characters or integers, it has the same functionality. So we might want to create a generic type for lists. And so this is where parametric types come in. We can create a data type with a list, with the name list, and a type parameter A. And what this is saying is that we will be able to create lists of A, whatever A may be. Integers, characters, strings, colors, points, anything. And in the generic case, we have an empty list, nil. Then we can cons something of type A, an integer, for example, to another list of A's. These need to all be the same A. So if we have a list of ints, we can't somehow have a character in here. But then we can create my int list prime that's a list of integers, and it's cons of 1, 2, 3, nil. And then we can also have a list of characters, cons of A, B, C, nil. And then we can write generic functions that work regardless of what is being stored in the list. So for example, length. Length takes a list of anything and is going to return an int. It doesn't matter if the elements of the list are one or another type. So how do we write this? Well, I would start by saying, what's the length of an empty list? That's just nothing. That's 0. And then we can say, what's the other case? Well, the other case is that we have a cons constructor with an element. The element itself doesn't actually matter. And then some list. And this would be equal to 1 plus length of the list. So we can recursively call this function, adding 1 each time until we get down to the empty list. And we can check that we have a good solution. Look at that. One thing you'll notice is that I do have these single quote marks in my variable names. Haskell is totally fine with that. It's not as strict as other languages on this particular case. And so then here we can see that we can actually compare the lengths of these two functions, of these two different types of lists, just as you would expect you'd be able to. You can also have multiple parameters. So before we had a list of anything, here we have an either construct. And the point of this is to allow you to either store something of type A or something of type B. And so we can create a division function, a safe division, that takes in 2 integers and returns either a string or an integer. And so if you try to divide by 0, it's going to return a string, specifically a left string, which is an error message. Or if you don't pass in the 0 as y, it's going to give you a right integer. And so we're saying, and this $sign you can ignore, it's the Haskell way to write it. We create x divided by y and wrap that up in a right value. This is one way to do error handling. It's not the suggested way, but it allows you to construct a similar approximation of what error handling might be like. So getting on to some of the last features here, Haskell is a lazy language. That means you only evaluate something when you need it. So you can, for example, create an infinite list of integers. And so long as you don't iterate infinitely on that list, that's fine. You can also create an infinite loop. This is infinite recursion. Forever x is equal to forever x. So long as you never call forever x, no issue. So here we could say, if true, give me 3. Otherwise, compute forever at 4. That just means 3. This does allow us to do some nice things, like set variables as undefined, so long as we aren't using them, or set things as errors, as long as we aren't using them. This can help with your code organization and pre-planning of how do you want to set up your structures, etc. We will talk about monads in Haskell later, but that's not today. All right, the last thing to cover is the where clause, which you will see in the programming assignment. So here, what we want is we want to define some new auxiliary variable that we will use in our predicates or in the final definition or anything like that. So we want to compare the square of x and y, and if y is greater than z, return bigger. But you would say, hold up, what's z? We haven't defined z. We didn't set it out here. It wasn't one of our parameters. That's where the where comes in. So y is greater than z, where z is equal to x times x. And so this is an auxiliary variable that helps us keep things organized and not cluttered. Right, so that's a 45-minute introduction to Haskell. We'll be working with this language for a little while, so I recommend starting to get comfortable with it. Being comfortable with your interpreter is particularly helpful. So knowing :R to reload, :T to give you the type, and then perhaps most importantly, :Q to actually exit GHCI. All right, with that, hope you're having a good day. See you on Wednesday.